Okay, good morning, everybody. I hope everyone's having a wonderful day. So a couple of quick things before I get started. Just remember, assignment 4 is due by the end of Friday. Keep in mind there's the 8:30 rule in effect. The other thing, if you have any questions or specifics, feel free to bug me during my office hours or send me an email. I'm very happy to help. I try to make myself very available for students. And I'm usually quite quick with responding to things, so just keep that in mind. But with that being said, I want to get right to the topic today. We're going to be moving on to talking about analyzing recursive algorithms. So I consider this one of those things that you're going to pick up from this course that I usually like to go a little bit more deeper with than perhaps some other professors will. But I'm hoping the things that you see here will be very helpful in your future, depending on if you're analyzing what kind of recursive algorithms you may run into. So here's the idea. When we analyze the running time of a recursive algorithm, very often we represent the running time as a recurrence relation. Now, in the past, we've actually analyzed at least one recursive algorithm. For example, we looked at DFS, for example, and I showed you some tricks that we often can use to analyze a recursive algorithm. We're going to use a lot of those ideas here, but I'm going to take it an extra mile. So when I do that, I'm going to talk about this thing called the recurrence relation. It's just a function that is represented in terms of itself. And the ones that we're going to be really interested in typically have a form that looks like this, where I have t of n, and there's two parts. The first case is where I have a constant a constant b, and I have t of n over b multiplied by a plus some function f. So that's why if n is greater than 1. Otherwise, I have some constant d if n is equal to 1. At first, I'm going to show you some simpler recurrence relations, and then we're going to build up to something more like that form. And then as we work up, I'm going to give you some people call them cookbook approaches to dealing with these types of recurrence relations. Like I said, I'm going to show you how you can build these recurrence relations as well. So you have an idea of like, okay, well, how do you get this thing? Because remember, like I say, when we do the algorithm analysis, we have to identify the case-based analysis we want to have. Usually it's worst case analysis. And then we derive some complexity function. That's going to be your complexity function over there. So when we see the A's and the B's and the F and the D, all of those are going to be things that are going to be represented within your analysis. So it might look kind of daunting with all these constants and stuff sitting there, but I assure you, when you actually play around with this in practice, those aren't going to be as abstract. They're going to be things that you're going to see, and all your job is just to identify them, and they often will be very helpful, especially with these two ladder techniques I'm going to show you. So we're going to see a bunch of recurrence relations. And my goal here is I'm going to show you 3 methods. So we're going to spend the next 2 to 3 lectures on these 3 methods along with an algorithm design technique called divide and conquer. So here's the 3 that I'm going to focus on is the so-called recursion tree or substitution method. So you may know this as iterative substitution. This is where what we do is we repeatedly apply the definition of the recurrence relation. We try to make a guess of a pattern for that recurrence relation. Then on top of that, what we do is we try to check it, and we often can with induction. But the thing is that this technique can be a little tricky to use when you have more complicated recurrence relations. Something that looks like this, unless you're a little bit more mathematically savvy, you won't be able to spot those patterns quite quickly unless you have some experience with them. So instead, I'm going to show you a different approach called the recursion tree approach or recursion tree technique that is more of a visual way of getting those good guesses from this substitution approach. You're going to see it's very intuitive, hopefully. And then the last 2 techniques we're going to focus on after that are the so-called simple master theorem. So some people call this the master theorem, but I generally like to show you a simpler one that's very easy to apply, but it has its limitations. When you can apply it or when you can't apply it. And then there's this one I'm going to refer to as the master theorem, which is a more general version of it that is harder to use, but it captures more complexity functions. It's a much grander cookbook But there's even more techniques that are more broader than that. I'm not going to be showing you some of those. Examples, one called acrobacy. That one involves computing an integral, by the way. I'm just kind of curious about that. So before we get there, I'm going to go through some concepts about functions that we're going to need to talk about some of these techniques. So the first one, so some of these you may have seen in a calculus class, by the way. The first one you may have, if not, that's okay. It's quite similar to something that you will have seen in a calculus class. And for most applicable circumstances, it will be something that you've seen in a calculus class at some point. Like I said, that stuff doesn't really go away. It's something that every once in a while rears its head. So don't just think it's just something in the past. It's something that every once in a while you're going to pick up and say, hey, this is actually kind of handy. So the first thing I want to define for you is something called an eventually non-decreasing function. So you may know what a decreasing function is, but may not necessarily know what an eventually non-decreasing function is. So this is a function f where there's going to exist some value, n0, quite similar to our big O notation definition, by the way, such that for all n greater or equal to this n0, it has to be that if I put in n, I know that the value of it cannot be greater than if I were to plug in the next integer that's higher than it. Now, you might ask, Dan, what the heck does that mean? So here's the simple way of talking about it. So when you have your function, imagine you plot it out. Well, your plot can go like this, for example, like a parabola, for example. A quadratic function most certainly will be eventually non-decreasing. It will be sitting at where n0 is in fact equal to 1. And every other point after that, because it's an increasing function, you can guarantee that property over there because every time you plug in another integer, you always know that the next integer is going to be sitting at a spot on the plot that's higher than the one that you had previously for the previous value of n. Now, here's the thing that makes this a little different, is that the function's allowed to wiggle around, for example, as long as it gets to some point where it starts behaving like that. So that's why the eventually means. So sometimes actually people call this asymptotically non-decreasing as well, for that same reason. And the name suggests exactly what we mean by that. There's some point n0 where the function, in fact, will behave like a non-decreasing function. Just to clarify, a non-decreasing function, it can have two common forms. First, you may know of things like increasing functions. So that's like your quadratic, for example. So you notice that if I look at any one point along here, that if I take, for example, consider, say, this point, if I check 1 point higher, it's always going to be greater of a value than otherwise. That's what we call an increasing function. In contrast, a non-decreasing function is allowed to be flat. So, for example, you can have a function that looks something like this. Notice that it plateaus like this, and that's okay, because it just means that it's not, the plot doesn't zig down, it stays flat or goes up. What makes the eventually part of this definition is that the plot actually can look something more like this, where the function can wiggle around a little bit, and then it starts behaving like one of these two functions. And that point where it stops, anywhere after that point, you can call n0. So to you, this might look quite similar to the ideas we've seen with big O notation, and that's exactly kind of the intuition you would want to use here. So usually from a calculus class, you'll be familiar with these two, or at least this one most certainly. Now the great thing about us is we don't actually have to do a lot of work to get functions that look like this, because almost every function you're going to run into in algorithm analysis typically is an increasing function or a non-decreasing function. So for example, a polynomial. Polynomials, your typical polynomial that as long as it's positive all times, typically will be some point where it's going to be so-called eventually non-decreasing. But if you have a function that's always going to remain positive at all times, and it always is increasing, then most certainly it's going to be increasing everywhere. So a lot of the functions that you're familiar with will have the fact that it's increasing already. So for example, log n is an increasing function, n to the k for any positive k constant. So that's, sorry, greater than 1, just to be, yeah, greater than 1 would work. But technically, if it was equal to 1, it technically would be something called it would be one of these non-decreasing functions, because it will stay flat all the time. But the point is that we're going to have this property. The great part is that most functions you're going to run into are going to have this property. So often I'll just take it as an assumption. However, if you ever find yourself wanting to check this, depending on how the function is formulated, sometimes you can pull a calculus to check, oh, it has an increasing function across the positive values. You may do something like that. Or another common way is using mathematical induction. So a lot of the work that we're going to do around this is not going to be really that apparent, because most of the time it's going to look like this anyways. Just be aware that if you ever find yourself really unsure, you can check it using induction typically. Another concept that I want to talk about is something called smoothness. Now, you may or may not have heard of smoothness before. This is actually a really I would say understated but valuable analysis trick and property that a lot of people tend to undervalue. So I like to show it usually. Is the following idea. So suppose I give you a function f. It has two properties. It's that it's eventually non-decreasing, so it satisfies this property. And it also satisfies the property that f of 2n, so notice that the input here is 2 times the input n. This is going to be big theta of f of n. So you might ask, Dan, well, what does that have to do with anything? I'll show you the neat trick that you can use with this so-called, if you know a function smooth. So it's worth noting that this comes out of some theory called B-smoothness, where instead of having a 2 there, you replace this with a B. There's an equivalency between B-smoothness and so-called smoothness that allows you to make a very simple assumption like this. The proofs for a lot of these things are based on induction, by the way. But the point is that we would like to have some analysis tool that I can make simplifying assumptions about the input. And that's really where the name smoothness comes from. Is very often I have it where I give you something like a recurrence relation like I had over there, but I usually have some assumptions about the input. For example, that n is a power of 2, for example. Or say if I want to make a simplifying assumption in my analysis, I want to say, hey, look, I'm going to assume that n is a power of 2. This is a very common way smoothness gets implicitly invoked sometimes. You're going to see why in a moment. So if you make assumptions like these, sometimes depending on if the function that you're curious about is smooth or not, you can in fact make these assumptions without restricting your analysis whatsoever, which is kind of wild. So that being said, are there any questions about eventually non-decreasing or what a smooth function is? I'm going to talk more about smooth functions for a little bit after this. So some of this you may have seen in a calculus course. Just the big thing to take away from this eventually part, as opposed to just being a non-decreasing function, is just going to be some point, we call it n0, that everywhere after that, it's going to look like a non-decreasing function, meaning it can go up like this, it can plateau, but it always goes upward or stays flat. And like I said, any non-decreasing function like this, this will contain the increasing functions too, right? So, because if they're always going up like this, it just means they're not plateauing at all. It just means that they're always going to go whoop. Or it might be some slower curve, but it's still increasing. Okay, so if we're good, I'm going to proceed to talk more about smooth functions. So you might ask, Dan, what can we do with this smooth function thing? And what are smooth functions? Like why would we care about that at all? And what kind of functions are smooth? Now, I have good news for you that most functions that you tend to play with in our algorithm analysis tend to be smooth. So very often you can just kind of use it very often. And you sometimes just get it for free, which is wonderful. Yes. Correct, yeah. So if, for example, if the function plateaus, you know it's not an increasing function, right? Because there will be some point where it's just like, oh yeah, no, it's not getting bigger immediately for the next n value. Yeah, exactly, exactly. That's the relationship. Exactly, thank you. So I want to just clarify a couple of things. So many functions are smooth. So I just want you just to be aware of that fact. So for example, constant functions. So if I gave you like f of n is equal to 1 or some constant d, you can know right away that that's smooth. So a constant function is most certainly smooth. If I give you log base 2 of n, this is smooth. Now I'm going to show you because when you look at this, you're like, okay, well, how is this smooth? Like, how do you prove that? Well, remember, what I've laid over there is, in fact, a big theta claim. Now, I must stress that if you only care about big O or big omega, you can actually use every property I'm going to talk about here, where you just replace the big theta with big O, if you only care about big O or you only care about big omega. I must stress that fact. So if you find yourself only caring about big O, you don't necessarily have to prove the big theta over there. You just have to show it's big O if you only care about big O. A lot of the results I'm going to present to you, I'm just going to present you with the big theta there, but the theorems or results will just be just as true if you were to put big O there or big omega. So I just wanted to stress that. Like I said, it's really a valuable tool. So let me just give you an example of how I can go about this. But I'm going to pick out a tool, since I've already talked a little bit about calculus anyways. Why don't I use that limit theorem I showed you earlier on in the course, just to illustrate how I could use it, seeing as I didn't really do any examples with that one. So why don't we try proving, this is proving, we're going to try proving that log base 2 of 2n is big theta of log base 2 of n. So this is the second property of what makes a smooth function. We know log n is in fact an increasing function, so we're okay. So we're going to be proving this using what I refer to as the limit theorem, not to be confused with the one that you've seen probably in a calculus class. This is the limit theorem for asymptotic notations. So all I'm going to do is I'm actually just going to use a limit to compute this. Now, I just want to give you a couple tips with this when you're using this, if you find yourself just offhand using this. So I'm just going to do this a little differently than we've done before, where I usually just throw the definition. I just want to show you just me using it once here, at least once. Why? Because it's a really quick way of checking things. And if you know how to use limits, then more the better. So you may recall that in the limit theorem, I say, okay, well, I would like to have some relationship between f and g. This is going to be my f, this is g. So what I would like to do is I compute a limit as n approaches infinity. I'm not going to be overly rigorous about this, just to be clear. Some people get very nitpicky about me putting an n here sometimes. That is for good reason sometimes if you're more of an analysis freak, kind of like me. So anyways, my point here is that I'm just having fun, by the way, just to be clear. So all I'm going to do is I'm going to compute this limit. It's going to give me, if the limit exists, it's going to give me some value, or it's going to tell me something. And based on that result, it'll tell me what the asymptotic relationship is between f and g. So if you're not sure about this, just go back all the way to when we showed you this, when we were talking about properties of asymptotic notations. So I'm just going to compute this out. So first, I'm just going to invoke the product rule of logarithms, because I have 2 times n. So I'll end up with log base 2 of 2 plus log base 2 of n. What's log base 2 of 2, everybody? It's 1, exactly, perfect. So then I have 1 plus log base 2 of n over log base 2 of n. Now, the great part is that, okay, well, the log n's, there's 2 of them sitting right there. And then I'm going to end up with something that looks like 1 over log base 2 of n. So I'm just going to have limit as n approaches infinity of 1 plus 1 over log base 2 of n. Now, the great part is that n approaches infinity here, and you know that log n is an increasing function, right? So it means that this is going to approach, what is this ratio approach? So what's going to happen to this? As n, it's going to tend to 0, exactly. So that means that when I compute this, because I just have a 1 plus something that's going to approach 0 anyway, so I just end up with a 1. So since 0 is less than 1 is less than infinity, if you look back at this, I gave you a whole bunch of different cases. This is one of those. So since I came up with a constant that's between 0 and infinity, this limit theorem tells me that log base 2 of 2n is in fact big theta of log n. I thought I would show you this, just so you could see it. Now, I have one important tip I can give you. Now, you may or may not have seen this trick in your calculus class. Sometimes it's shown in a second calculus course, but it often depends. Is if you ever find that this ratio never evaluates to anything meaningful, it goes to an indefinite form, so like 0 over 0 or infinity over infinity. You use something called L'Hopital or Hopital's rule. I'm not going to show you that here, and I'm not going to throw things at you that require that rule, by the way, just for the sake of clarity. I won't do anything like that to you. But if you know that rule, you can always apply a derivative to the top and the bottom separately, and then you just simply go and you say, hey, look, I got my new limit with these derivatives in the ratio, and I could keep doing this over and over again until I actually get something out of this limit. How do we go from log base 2 of 2n? So remember, this is right here. Remember, this is coming from the definition of smoothness. Remember, there's two properties. There was the first property that's eventually non-decreasing, and then the other one is I wanted to show that f of 2n is big theta of f of n. So all I've done is the 2n is right here. So that's why we were interested in this. So this is the second criteria for proving smoothness. So if I want to show that a function's smooth, I need to show this property. No, I won't. I will not get you doing crazy limits on the exam. Just to be clear, if I were to throw anything like this at you, it would be something very, very basic. Just to be clear, like I said, I'm not going to throw a lot of those fun tricks that you've probably seen in a calculus class where you like square the both sides, or I won't do anything like that. Just to be very clear. If I do, I'll just usually say it would be something very similar to probably a multiple choice question or something, and it'll be something really basic. But like I said, if I do something like that, I will be very clear about it on the exam format, okay? Who knows, I may not even examine this property, just to be clear. But I just want to make sure you see it at least once. We often will use this as a shorthand in this part of the course. Okay, so some other functions that you should be aware of are also smooth, are polynomials of the following form. So n to the k for any constant k greater or equal to 0. So that's a pretty wide class of functions. Now you might ask, Dan, well, what if it's n to the k plus some value? Believe it or not, it actually won't matter too much for us, that specific detail, when I show you the interesting property in question. But I must warn you that not every function is smooth. Just be aware of this fact. Not every function is smooth. For example, if I give you 2 to the power of n, an exponential function, typically exponential functions, they are not smooth. So 2 to the power of n, that's not smooth. You might ask, Dan, why would that be the case? Well, if you actually walk through this process, because you know exponential function is definitely an increasing function. It increases quite rapidly. But it fails actually the second property. It's because if you think about it from an asymptotic standpoint, when you insert that 2 in, you'll end up with 2 to the power of 2n, which most certainly is actually much greater than just 2 to the power of n. The gap gets too wide between these two types of functions. And that's why it's not smooth. If you find yourself curious about this, you're welcome to try proving it. But here's the main thing I want to talk about with smoothness that I want you to just be aware of. And this is something I call that often is called the smoothness rule. A lot of the theory that I'm going to show you is built around this smoothness rule. So here we go. So let there be 2 complexity functions. 2 complexity functions. 2 complexity functions f and g, where f of n, or sorry, f, just to be a bit more exact, f is big theta of g when n is a power of b. In fact, I'm going to be a bit more exact here. Is the power of an integer constant, b greater or equal to 2. But I must stress that a lot of the theory here easily generalizes to more bases that I'm going to refer to in a moment. So this is just the setup for this. So I have 2 complexity functions, f and g, and I'm going to assume that when I study and I prove this property, that it's only on n's that are a power of some b value. So for example, if b was 2, I'm considering when n is a power of 2. So it's something like 1, 2, 4, 6, 1, 2, 4, 16, 8. Like I said, it's Wednesday. 1, 2, 4, 8, 16, so on, so on, so on. Don't mess up your powers of 2. Those are kind of important. So now this is the part that's relevant for us. If f is eventually, sometimes, like I said, some people call this asymptotically non-decreasing, and g is smooth, then this is kind of the killer app of this. Is that you could just say f is big theta of g. That's unconditionally. So when I prove it this way, so if I assume that n is some power of b, and I show this property, if I know that f is eventually non-decreasing, then I also have g is smooth, then I can actually get this relationship without considering the input just being restricted to a power of b anymore. It happens just all the time. That's why we call it smooth. So if I were to prove some result for given values of n like this, and there's all sorts of different smoothness rules out there, but if you have a property like this, as we're going to see in some of the results I'm going to show you, you can actually straight up just say this down here without ever having to worry about anything weird in the middle. That's the power of smoothness. So are there any questions about the statement of the smoothness rule? I just want you to be aware of this. So sometimes when computer scientists or people that are analyzing algorithms more broadly, very often when they're trying to analyze algorithms, they sometimes implicitly assume this smoothness rule sometimes when they assume n is a power of 2. by the way. Just sometimes when people, for example, analyze binary search, very commonly they'll say, oh, well, assume n is a power of 2. And you'll ask, why do they do that? It's this. So I've shown you one of their magic tricks. So just be clear. Sometimes they do make this assumption without it being exactly this. So in those cases, they're restricting their analysis just for the sake of maybe teaching you something. But most certainly, this is a surprisingly undervalued tool in analysis, and only usually people that run into this usually will say, hey, look, that's kind of neat. We'll find it's very useful for recurrence relations because very often when we're analyzing algorithms, usually we assume n is some power of 2 or 3 or 4 to make it a little easier to analyze the algorithm so we don't have to worry about floor functions and ceiling functions. That's where we're going to use this. So are we all good with this? So that's all I have to say about smoothness. So if we're okay with this, I'm going to proceed to start talking about recursion trees. So like I said, the big thing about this smoothness rule is it is indeed that you get the cut corners, but you actually aren't, because this theory allows you to straight up just go in the middle and just remove that part. Can you please confirm the relationship you mentioned about increasing / non-decreasing? Okay, so remember, an increasing function will look something like this. This is, for example, a polynomial. If it's a log, it might look something like that. These are examples of increasing functions. A non-decreasing function, it's a little bit more relaxed. So in these ones, when I have an increasing function, typically the way it's defined is that, so if I have f of n, usually it's that if I plug in the next value of n, it has to be that it's strictly larger. Sometimes I must stress that in different analysis circles, sometimes they use the word strictly increasing as opposed to increasing for this, just to be clear. In non-decreasing, you relax this condition a little further. So instead it's just that it's less than or equal here, as opposed to just strictly less than. That's why we could say that every increasing function is a non-decreasing function. And the eventually part, the only thing about the eventually part is just that the function is allowed to wiggle around and do whatever it wants up to some point. And after that, it's going to start behaving like a non-decreasing function. As long as that point exists, we can call it eventually non-decreasing. But yeah, for most of the time we're going to talk, it's pretty much going to be that these are asymptotically or eventually non-decreasing. But anyways, so let me proceed to talk about recursion trees. So these are kind of the first tool I'm going to show you. Now, you may have seen before in your past, possibly solving recurrence relations. That's another tool that you could technically use here as well. This is just another way of casting a lot of the things that you would do over there, but it's very intuitive, at least I think it is. But you might agree or disagree with me, and that's okay. So we're going to study things called recursion trees. So this is just another analysis tool for us. So just as a reminder, actually, let me just write one quick thing here. So often, when we devise recurrence relations, for the running times of recursive or divide and conquer algorithms. I haven't yet talked about divide and conquer algorithms. I will in a couple of lectures. They're a very specific kind of recursive algorithm. I'll give you a heads up. It's going to look exactly like that. Like usually their form looks like the recurrence I showed you at the beginning of this lecture. we do the following. Usually this is typically the way it goes down. First step is you derive some recurrence relation. So this is often the part that relates to most of what we've seen before. So this is you deriving your complexity function based on the analysis of the algorithm. So remember, very often what we did was we ignore the recursion, and then we counted up all the operations, right? For all the non-recursive work. I'm going to kind of whittle this down a little further today. So once you have that, you're going to figure out a closed form. Remember, this is just some formula. It may even just be the sum itself before you simplify it down. And in some circles, they like to call this a guess, because usually what we do is we take advantage of our pattern-seeking ability to try to guess what the closed form looks like before we try to attempt to solve the recurrence relation or apply one of these analysis techniques. So sometimes people call it a guess. So the technique I'm referring to is sometimes called guess and check. I'm just showing you an intuitive way of approaching this. So need to check our guess. One can use induction to do this. So this step I'm going to omit just because, just for the sake of time, but at the same time, I'm going to include one example in the notes of a rather nice and simple example, but I won't ask you to do this on an exam, for example, just to be clear, because there's only so much time. And then lastly, what we did normally is we determine the asymptotic behavior. Of 2. So this one right here. This is actually what we've been doing a lot of the time when we've analyzed recursive algorithms, just we've been taking advantage of properties that things like trees have. So when we did, for example, the analysis of that computing the height, for example, when I did that, took advantage of properties of the tree, so I didn't actually explicitly throw this out at you in the first step. We didn't really need to do it because there's nice properties that we had about the trees. We're going to do something kind of like that here, but this is a rather general kind of pattern-seeking approach you can take. So I'm going to walk us through this process with a simple example you may have seen before, just so that we're all clear how to do this. So the recursion tree method, so just to be clear, the recursion tree method helps you get good guesses. That's the way I like to put it. It helps you get good guesses. Why? Because we know a lot about trees, so we're going to try to take advantage of the properties of trees. And fortunately, because trees themselves are technically recursive structures in themselves, they quite work naturally for modeling things like recurrence relations. So later on, I'll show you some more cookbook-esque approaches for things, but here you're hopefully going to find some intuition when we're going to do this, okay? So I'm going to do one example here, and then depending on how much time we have, I'll do a second example. If we don't get to the second example, I'll have it in the notes for you to take a look at. And I also included another simple example like this one. So let's proceed. So we're going to start off with a very basic example. We're going to talk about computing factorial. So for some of you, this will be like, Dan, I know how to do that. So we're going to talk about computing n factorial. So I'm just going to care about it from the perspective of a positive integer, but I will mention, of course, that you can also define it for 0 as well. given any positive integer, n, and factorial is in fact equal to n times n minus 1 times n minus 2, all the way, there's all these products happening until I get to 2, then 1. And note, oftentimes it's the case that, that 0 factorial is equal to 1. So we're going to design a recursive algorithm that computes factorial. Now, you may or may not have seen this before. Have you seen this before? Let me know in the chat. So I'm hoping I'm going to kind of allude to some connections between recursion trees and some other analysis techniques. So if you haven't seen it, that's great too, because I'm going to walk through this. So let's, wow, that's pretty epic. That's pretty epic. So if you think about this definition, if you look at n factorial, you'll notice that it's n times n minus 1 times n minus 2, and so on all the way down. Now, you can actually write n factorial recursively as well. So you could write it like this instead. If n is greater than 1, then n factorial is actually equal to n times n minus 1 factorial. So notice that if I do this, n minus 1 factorial by this definition is just n minus 1 times n minus 2 all the way down to 2, then 1, right? So this is in fact a recursive way I could actually define n factorial. Otherwise, just to cover my butt with that over there, otherwise, I'm just going to assume it's equal to 1. So for example, 1 factorial is equal to 1. So once you have that, you quite quickly could see how you could design a recursive algorithm that does this. So here's an algorithm for computing factorial. So as input, it's going to take a non-negative integer, but for our purposes in our analysis, we're just going to assume it's positive. So it's going to be a non-negative integer n, and it's going to output n factorial. So just to be clear, by the way, if it's been a little while since you've seen n factorial, or if you've never seen it before, so for example, if I have 3 factorial, this is equal to 3 times 2 times 1. So this is, of course, 6. So when you view it like this, what we're going to do is we're just going to transcribe what I wrote over there recursively into my algorithm here. So I'm going to have an if statement. So I'm going to say if n is greater than 1, then, now this is going to be my recursive case. So usually a natural way to think about recursive algorithms is by breaking them into a recursive case and a base case. This is very helpful oftentimes when you're actually analyzing the algorithm as well, as we're going to see. So I'm going to return. So in this case, I'm just going to compute this right here. So all I do is I take n and I multiply it by the result of fact of n minus 1. Because that's all it is just this right here. And then we have the base case. So we have a base case. We're going to return 1. Like I said, it's a really basic algorithm, right? Are we okay with my algorithm here for factorial? So if we're okay with this, let me proceed. So when I do the analysis here, there's kind of 2 pieces you need to take into consideration. I'm just going to quickly note this just for the sake of time, but I go into more detail in the notes, just so take a peek at that. So when you formulate the recurrence relation, there's two main parts. There's your recursive case that you need to consider. And then there's the base case. So the recursive case and the base case. So in this one, you're going to count all the non-recursive work, just like we did before. So all those operations where you ignore the recursion. And then, of course, you need to take into consideration the so-called recursive work. So this is, remember when I talked about, like, when we did the tree-based algorithms or DFS, for example, I made and took advantage of properties that the structure had. For example, the tree. This is what I'm referring to here, the recursive work. So what I mean by this is things like, is it being broken into multiple subproblems? How big? Because sometimes you're halving it, sometimes you're chopping it up into 3 pieces. Sometimes it's a little unclear. So usually it's a good idea to have both of these in place so you know you have identified both of these. You're going to find that when we formulate the recurrence relation, both of these are going to be accounted for in the first part of the recurrence relation. The second part here, this is almost always going to be constant. So you just analyze when the base case is met. I must stress that this is usually constant. So let me just quickly analyze this. Then when we come back next time, I'll actually do the recursion tree example. We didn't quite get to it, so I'm going to do it in class next day. So don't worry about reading ahead in the recursion tree notes, but I will post it there if you want to get a little ahead of the game. So let me analyze this, and I'm going to use this framework here to help me. So first, we have the non-recursive work that happens whenever n is greater than 1. So when n is greater than 1, now I must stress also one other thing. Sometimes when you have a recursive algorithm, not everything in the algorithm is written in that if statement. Sometimes there's stuff that happens afterwards. You need to take that into account as well. So remember, just assume that you look at the recursive case and see what the algorithm does in that recursive case. So here it's very nice and simple, right? If I ignore the recursion, so remember we want to ignore the recursion. So ignore the recursion in this recursive case. So in the recursive case, each one of my recursive calls is going to be treated like some constant because all I'm doing is passing a number along. And then I have it where I multiply it by n, and I have this if statement, right? So whenever this happens, regardless, all of this is going to take constant time. So I just look at when n is greater than 1. It just takes constant time, right? So when we think about this, we have two parts. The non-recursive work. So this part, I'll label this as A. And this recursive work. Then we have B. So the recursive part, so I'm going to represent this running time as t of n. So notice that in the recursive part of this, remember, I make one recursive call. It decrements n by 1. So there's only one recursive call that happens. So I'm going to write this. So this is actually my B part right now. So that's the B part. So this is representing the one recursive call, and it decrements n by 1. And then I have all of the non-recursive work that happens in the recursive case. That's what I have for A, right? But remember, like I just said, that all takes constant time, right? So I could write this as a 1, for example. But if you really just don't like that, you're welcome to write a constant times the 1 or some other constant. Or you can even write big theta 1 if you want to be a little bit more careful about it. I'll usually just write a 1 because it's not going to make any difference for the analysis. But if you want to be careful, you're welcome to add more details. So this is what happens in the recursive case. We have one recursive call. And so this is what's happening with the recursion. This is the non-recursive work. So this happens if n is greater than 1. What happens when n is equal to 1? Somebody quickly tell me. How many operations happen? It's some... It takes, yeah, just 1. So I'm just going to write that as a 1. Like I said, if you want to get fancy-pantsy with this, you could also write it as some constant d or whatever. Like I said, it won't make much of a difference, at least from an asymptotic standpoint. Remember, like very often when we analyze the algorithm, since it's some constant number of operations, you may as well just treat it as a single step. So this is actually how we could formulate the, so this, by the way, this is the base case. Just like I have in my algorithm. See the two parts? So here's the recursive case. There's the base case. So anyways, with that being said, we're going to stop right here. When we come back, we'll talk about recursion trees. I'll do a couple of examples. And then, depending on time, I may just show you only one of the two master theorems. So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.